We appreciate you joining today's webinar, Why CAD Geometry is Not CAE Geometry. Today's presenter is Mark Cammon. Mark is the Technical Director at ITI Limited, based outside Cambridge, UK, and he's also the Product Manager for our advanced geometry processing tool, CADfix. Thanks for joining us today, Mark. I'm going to go ahead and turn things over to you.
Okay, thank you, Marco, and thank you for everyone for joining today's webinar. So let me get going here. Okay, so a little bit of background about myself. So I started off my career as an aerodynamicist in the military aircraft industry in the UK, 4 years processing wind tunnel data, flight test data, and learning how to use computers to crunch that data. Quickly realized that actually computers helping engineers was really what excited me. And so for the last 26 years, I've been working here in Cambridge, primarily on the CADfix product, aiming to sort of make the life of simulation engineers and the geometry they have to work with easier. Okay, so today's webinar is, I've broken it into two parts. So there's a sort of a mildly depressing first half where we'll go through all the problems that CAD geometry causes us, and I'll try to elaborate some of the reasons why. And then the second half will be a bit more uplifting, where I'm going to pick a couple of the areas of research and development that we're doing in CADfix to try and address some of these issues with CAD geometry. So just before I start on that, a bit of background behind CADfix for those who aren't familiar with it. So CADfix has been around for 41 years this year. So it started back in the late 80s. The company had a different name back then. It was FIGS Limited, and CADfix had a different name as well. It was FAM, which stands for Field Analysis Modeler. And there's a lot of clues in the name there, because back in those days, a lot of the simulation was done in a single package. So the actual geometry, the modeling of the geometry was done in the same tool that was actually doing the mesh generation. And so in those days, CADfix was really quite good at creating very complex hex dominant meshes of geometries, as you can see on the screen here. But around about sort of the end of the 80s, early 90s, then sort of commercial CAD systems really started to take off, and geometry started to be created outside the simulation environment, and people were receiving geometry as IGES files or as native CAD geometry, and they had to do the simulation on this much more complex geometry. So the sort of meshing that we were really focused on back in the 80s, highly structured hex dominant meshing, that becomes very difficult to do as the complexity of the model goes up. And so the industry as a sort of whole really sort of tackled this complexity issue by switching over to automatic tetrahedral meshing for a lot of structural simulation. And so we did the same thing. We introduced tet meshing within our tools, but there was a lot of other tools were also coming into the market at this time offering automatic tet meshing. So it was quite a straightforward technology to develop. And so we were sort of starting to lose out on that front. But what we had noticed during those years really was that as the CAD geometry became more and more prevalent, the quality of the CAD geometry was becoming an issue, and not just the complexity of it, but actually integrity of it was an issue in the early years. And so we took about the end of the 90s, we took a strategic decision within the company to sort of change the direction of our product and switch over to more of a geometry focus. Initially, it was focused on developing algorithms for cleaning and healing and repairing CAD geometry to enable you to actually translate it or move it between different CAD systems. But as years went on, the CAD systems improved that translation themselves. Their exports became better. STEP as a format came along. That removed a lot of the issues with translation. And so we started to decide what to do next. So we still had this eye on the simulation market, and we could still see the simulation engineers were struggling with the geometry. Even though it was cleaner, they could get it into their system, they were still struggling to actually do the simulation. And at that point, we sort of decided to invest in several strategic geometric algorithms. So some research we did in collaboration with some universities here in the UK. On one of the topics we looked into is this thing called the medial axis transform, which you can see on the screen here, this sort of nice rainbow colored, sort of like a thickness distribution of a solid body. So we started to invest in these advanced geometry processing tools with the goal being to try and ease the pain that the simulation guys were still seeing when trying to process more and more complex geometry. So that led us into a whole range of new developments, which in the last sort of 15 years has also included mesh generation again. So we now really have activities spanning the whole spectrum of advanced geometry creation from CAD. So we have toolpath generation, you can see at the top there, we have partitioning, going all the way down to advanced mesh generation, and again back into the hex dominant mesh generation problem, which is still sort of the holy grail. So that's a bit of background as to where CADfix came from, where the company has its history. So we maybe a surprise to some of our existing CADfix users is we have this legacy meshing technology strength. Personally, I think my interest in 3D geometry and simulation I can trace back to Christmas 1982 when I got this, my first computer there, you can see on the left, and a game, 3D Monster Maze. And you can see that little animation on the right-hand side there. So that really sort of fired up my 15-year-old mind and really got me wondering, well, if computers can think in 3D, and just what's the hardest question they could answer for me? And that really started my career in sort of geometry engineering and trying to get computers to do hard things. Okay, so that's a bit of a background. So looking at the structure of the webinar, as I said, I've broken it into these two sections, and we'll have a poll in the middle where we can assess the first half and get your feedback on that. So before I sort of launch into describing the detail of the CAD geometry, I need to explain some of the terminology I'm going to be using here. So starting with the CAD geometry, what do I mean by CAD geometry? So for this webinar, I'm really talking about the sort of output you get from commercial CAD systems like CATIA, NX. So it's typically trimmed, NURB surfaces, curves. It uses a boundary representation to define the geometry. You find it in single parts, multiple parts, or very complex assemblies. So this is what I'm calling CAD geometry for this webinar. Just to show what isn't CAD geometry for this webinar, because there are other alternative forms of geometry. So faceted surfaces, explicit surfaces, subdivision surfaces, untrimmed surfaces, and point clouds are all examples of alternative geometry forms that I'm not calling CAD geometry here. So just bear in mind that this is really commercial CAD software geometry that I'm talking about. So what do I mean by CA? So this is a bit easier to define. So it's using computers to simulate any laws of physics, so thermal, stress, fluid flow, electromagnetics, and so on. So they all have this common theme that they typically start from a 3D geometry definition, and they require some discretization of that geometry in order to solve the physics that they're solving. So you might be thinking, well, CAD systems already offer an integrated CA capability. So you can do some simulations within a lot of CAD systems. So I'm not talking about that sort of CA here. I'm really talking about advanced CA as being the thing that's suffering from this geometry. So what do I mean by advanced CAE? So I'm talking about any sort of CA that's currently limited by either human resources or compute resources. So by human resources, I mean simulations that still involve a significant amount of human effort to prepare the model, so cleaning the geometry, meshing the geometry, or human effort to actually interpret the results and influence the design by interpreting the results of a simulation, or any other thing that involves some human being in the loop. On the compute resources, this is a bit easier. So any sort of simulation that is really currently restricted because it runs too long, it uses up too much memory. So some examples to put this into context. So jet engine failures are a very common example of what I would call advanced CA. So trying to simulate the fan blade coming off of the front of the engine, or a bird strike, or in fluid flows, so simulating transonic flow, shock waves, turbulence, or electromagnetics is another example. So trying to simulate lightning strikes, predicting the current flow across and through aircrafts, antenna performance, and so on. So these are sort of things that I'm calling advanced CAE, and physically this is how they are simulated or tested today with expensive physical tests. A fan blade off on the left there, wind tunnel on the right for the fluid flow, some sort of electromagnetic test environment there on the bottom picture. So these all can be tackled today. There are solutions and simulations going on for these things, but they fail my criteria in that they're either limited by human resources. So, for example, the fan blade off model on the left there can take weeks, many weeks to actually produce an efficient model you can actually run for that simulation. And some of the CFD tools are pushing the limits of machine memory and storage and so on. So they are tackled, but they're not tackled to the level we actually want. Okay, so what do I mean by CAE geometry then? So CAE geometry is geometry that enables fast and efficient mesh generation. So there's a discretization problem that is common across all CAE. So this is the obvious requirement for a CAE geometry, is it has to enable meshing to be done very efficiently. But there's two other aspects of my CAE geometry that are important. So adaptive mesh refinement is becoming a more important aspect of solvers these days, being able to modify the mesh as the solver converges on a solution. So in order to do that, you need to have the mesh coupled with the CAD so that you can actually refine the mesh directly on the exact CAD geometry. So that connection is a really important aspect of CAE geometry. And lastly, once you've performed some simulation, you have some results in a mesh format, you need to be able to get this back into a CAD system for either manufacturing or for sharing through other workflows that typically expect to start from a CAD definition of the geometry. So true CAE geometry has to be able to satisfy these three criteria. Okay, so those are the terms defined. So if we now start to move on to why is CAD geometry not CAE geometry, I've identified 10 issues here. But before I got started, I realized that actually there was an underlying issue, a zeroth issue that myself and others probably take for granted when they talk about working with CAD geometry, and that's that it's not geometrically watertight. So the way that the CAD solids are created today, they're defined as a patchwork of trimmed surfaces. So individual surfaces are stitched together to give you this sort of outer shell of your solid, and this sort of stitching process is not exact. So there are approximations involved in the intersections between surfaces, the trimming of surfaces and curves. So the end result is that the geometry is held together by a tolerancing system in one form or another. So it varies from CAD system to CAD system. But all these sort of junctions and joints between faces, they're held together by some tolerance or other. So here's a sort of a simple example of a couple of trimmed surfaces. So the surfaces are in blue. The trimmed nature means that the grey face is actually the piece of that surface you actually want to use in your aircraft. So we're not using the whole of the blue thing, we're trimming it with some of the curves. And where those curves are shared between two neighbouring faces, then that junction is where all the approximations come in. So this is sort of an example of where maybe the vertices and the edges at those junctions are not exactly on both trim surfaces at once. And so we have these tolerances that actually define when the object is watertight. So this is sort of an underlying problem, which for mesh generation you might not think is an issue, but actually when you start getting down to making very, very fine meshes, you can start to fall into the realms of these tolerances, and then your geometry starts to look a bit more like this from a meshing algorithm. So there are clear gaps start to appear between faces that your meshing algorithms then start to fall into and trip over and so on. So just bear this in mind as we sort of go through the next problems, that this is underlying all of them, this sort of robustness of the whole CAD representation. Okay, so moving on to number one, the first problem we've got. So I'm calling it a dumb solid. So by this I mean that the geometry of a CAD solid is only defined on the skin. So we only have curves and surfaces defining the outer boundary of your solid. CAD solids don't give you any information about the shape of the interior, the proximity of various parts. So if you're writing algorithms to walk around on the interior of a solid, then they're typically sort of stumbling around in this sort of dark area with only the outer surfaces to work with. So this is a problem for CAE when you come to discretizing or meshing volumes, which is a very key activity. And algorithms that need to discover proximity do it in a very sort of clumsy or expensive way by touch. So by firing rays, by detecting when collisions occur in the meshing process. So here's an example of this and how it affects the meshing quality. So the solid in this case is actually the air volume around the aircraft, and we're trying to mesh the air volume to do a sort of fluid flow simulation. And the goal is really that the mesh next to the skin really needs to be very fine, very well controlled, very structured. And so the meshing algorithm used here is growing layers of mesh away from the skin of the aircraft. And you can see in the nacelle pylon wing junction on the right-hand side there, where this sort of simplistic marching approach, the advancing front approach, you get collisions between the various fronts coming off those pieces of geometry in that junction. And it's very difficult to resolve those because you didn't see them coming. So you had no pre-warning that you were going to collide into those, and so it's very difficult to resolve them. And so typically you end up with some sort of compromise in the mesh where the structured mesh you want stops, and then this sort of lower quality unstructured mesh has a sort of leak in to fill the gaps. So that's sort of an example of the missing proximity, the fact that the solid is really quite a dumb solid. So for these 10 problems, I'm going to highlight what I'm calling a CAE geometry challenge. So this little red line at the bottom of the screen here. So I'm going to pull these things out, and we'll use them at the end to sort of summarize the issues that are causing problems with the CAE geometry. So for this one, I'm going to say that we need to have a smarter proximity reasoning for CAD solids. We need to have better than just walking around the skin and sort of firing rays to tell us where the thickness is and where the proximity is. Okay, so that's number one. Number two is complexity. So here's an example of quite a complex piece of CAD geometry. This is sort of zoomed in a region. So you can see there's a lot of detail going on there, a lot of blending, a lot of complex shapes, a lot of realism has been captured by the designer in this model. And if realism is what you're trying to capture, then it's done a very good job. What typically happens though when the simulation or the analysts receive this geometry, they see how that CAD geometry, how the skin of that CAD geometry actually was, how it was pieced together, what all the individual faces were stitched together to make that nice solid on the left-hand side. And that's when you start to see some of the really nasty artifacts coming out of the CAD systems when they make this complex geometry. So you zoom in onto some of these areas on this model here, you can see how the CAD system has created some very short edges, some very skinny faces, very tiny features in the skin, which were quite surprising for the CAD designer because they didn't realize this was happening. They were just constructing their model, and this was all happening under the bonnet. But the simulation guys typically have to deal with this because they have to mesh the skin of this solid. So why does this happen? Why do we get this coming from the CAD systems? So there's a couple of reasons. One of them is sort of going back to the way CAD systems interface with humans, and they tend to replicate the sort of the human machining operations that we're all familiar with, so extruding, cutting, sweeping, rounding, and so on. And they allow you to compound these things together, so you can overlay all sorts of operations one on top of the other. And that is one reason why you end up with a lot of complexity in the skin, because of all the overlaps and interactions of these operations. The other one is because of the underlying maths that holds the whole system together, the whole trimmed surface, all the tolerancing I was referring to earlier on. In order for those maths algorithms to actually work robustly and for the CAD systems not to fail operations, they enforce very strict conditions on what's the shortest line you're allowed to have, what's the curvature change you're allowed to have. And in many times, to satisfy their own rules, they have to introduce small features in order to satisfy their own rules. So that's another reason why we get these. And as I was saying, they influence the CA process because of the mesh generation of the skin, often being very badly affected by the way that the skin is defined. So I can see a couple of challenges coming out of this particular problem. So being able to automatically simplify CAD geometry. So that's something we've been doing with CADfix for many years. Allowing our users to join these faces, collapse small edges and so on. And also we're now moving into non-destructive ways of simplifying the CAD geometry, so virtual topology, for example. So that's one way we can modify the CAD geometry. The second way we could do this is to actually make the mesh generators smarter, to actually get them to ignore a lot of these sub-resolution features, just automatically mesh over them. So two challenges from this one. Number three, it isn't the right bit of geometry. So this is easiest shown as an example. So an assembly model here, when we want to do a fluid flow around this assembly. So it could have thousands of bodies. The bodies are in contact. So if you're looking for the wetted area, which you want for your simulation flow, that wetted area geometry is not defined in the CAD system. You have to extract that. You have to derive it from this very complex collection of bodies that are in contact. Some of them may be actually penetrating. Some of them actually have small air gaps between them, so it becomes very difficult to actually extract the geometry you want to do for your simulation. Another example, given a single body, The body is represented in the metal, but you actually want to do the simulation of the airflow. So again, the actual geometry that you need to mesh isn't actually part of the CAD model. It's something you have to derive from that. So the challenge from this one is an automatic domain geometry extraction facility for very complex parts and assemblies. Number 4, so the CAD geometry can be too realistic. So this typically happens in CAD models that are very close to the sort of the end of their life. They're down at the manufacturing level where they're being produced primarily to drive the manufacturing process. And so typically they collect a lot of realism. They collect a lot of nuts and bolts and company logos and instructions, and very small, high fidelity realism features creep into this. But they can cause big problems for the mesh generators, because they typically are below the sort of resolution you need for a simulation, or they're below the resolution you can afford. They would drive too much mesh into your mesh, and so you have to come up with a way of removing these. So there's a couple of ways I can see doing this. So automatically defeaturing the geometry. So again, stuff that we've been working on in CADfix for many years to try and give people tools for identifying and removing this sort of geometry. But again, the mesh generators need to play a role in this, I believe. So meshing needs to be able to have a sort of a user-controlled level of detail where you can say, I'm not interested in features below this size or below this curvature, and the meshing generation algorithms would walk over those things automatically. So there's a couple of challenges coming from this one. The next one is the opposite, really, so too idealistic. So this again happens at the other end of the design spectrum, typically with sort of preliminary design models, early design models, where you don't want all that realism because you're not about to manufacture it. And so this can cause problems with this sort of feature happening, where the geometry is constructed from more primitive type features, so cylinders and blocks, and you're gluing them together. And because of the lack of those nice fillets that give you the realism, you end up with sort of unmanufacturable features creeping into the CAD geometry. So some examples here on the left. We have a face there that has a very, very sharp, spiky corner at the end. On the right, we have sort of two primitives that are being glued together, but just on the overlap, there's a very tight crack underneath the edge there that, again, is going to cause difficulties for meshing these geometries. So the challenge for this one, I think, is really on the doorstep of the mesh generators, because I don't believe that the CAD systems are likely to provide tools for this, because this is fundamentally correct. What you see on the screen there is what the user asked for. So the mesh generators are the guys that need to be able to cope with this sort of too idealistic problem. Okay, number 6, so no idealization. So this is a special case really where we have geometry that can be simulated much more efficiently if we can approximate it with a sort of a mid-surface mesh rather than a complete solid mesh. So the example on the screen here is a thin-walled aerospace component, which you could mesh with TETs, you could mesh automatically with TETs, but you'd have a lot of them. If you are able to construct a mid-surface mesh as an approximation, then you can get a big speed up in terms of the simulation time, and the number of degrees of freedom drop dramatically. So it's a very attractive goal, being able to idealize solids into sheet approximations. But the trouble comes back to the lack of proximity, sort of the whole dumb solid problem again, in that CAD solids find it very difficult to reduce complex, or not even complex, even fairly trivial thin-walled objects into mid-surface approximations robustly. So there's a lot of tools out there that will do this semi-manually, so they allow users to pick pairs of faces and it constructs a mid-surface and so on. And the user then has to manually sort of stitch together the mid-surfaces. And where the thickness becomes variable, then that becomes quite a challenge to construct a mid-surface there. And obviously that brings a human back into the loop and breaks the sort of the whole optimization goal. So the challenge coming out of number 6 is quite obvious. We need a way of automatically creating robust mid-surface idealizations from CAD solids. Okay, number 7, no partitioning. So this sort of refers back to my history of CADfix and how the structured hex-dominant meshes were the first things we worked with back in the beginnings. They were the easiest meshes to create. Even today, hex-dominant meshes or complete hex meshes are often considered to be the gold standard of mesh. You'd really like to have one of these, but you tend to compromise and accept a tetrahedral mesh because of the automation you get. So to achieve a hex mesh today, starting from a very complex CAD model, then you always have to use some sort of human intervention to chop up the complex solid into these smaller blocks, which can be then meshed with hex mesh. So CAD geometry doesn't really support this whole idea of sort of subdividing a single body into lots of little pieces. So there's no support for this sort of connected multi-solid representation of a body. There are specialist tools out there for enabling this subdivision, this blocking of CAD geometry, so things like IsomHexa and Qubit. They're very proficient at allowing users to sketch the blocks and construct this sort of block topology very quickly. Again, they're quite labor intensive, and they bring a human into the loop, so they really rule out any sort of optimization goals that you had. So the challenge coming from this one really is we need to be able to automatically partition complex solids into hex meshable blocks. That's the challenge from this one. Okay, number 8, so limited shape optimization shape. So this is so using simulation to optimize shapes is a really powerful concept. But when you are constrained by the parameters within the CAD model as to what changes you can make to your mesh, then things become quite limited. So this example here, for example, so the hole through this is a cooling hole from some sort of turbine blade. As this is defined in the CAD system, that hole will always be circular. It's a cylindrical thing with a radius. The plates will always be parallel, and so on. So if your simulation actually comes back and says this is the optimum shape, then this is you can't achieve this by modifying the parameters on the left-hand side. There's no way you can go from one to the other. So what we need here is the ability to reparameterize CAD geometry to give it handles or optimization handles to allow the optimizers to actually achieve or drive the correct geometrical functions. So if you think of the wetted area of a ship hull, for example, then you might want to optimize or minimize the wetted area. That's not a parameter you can control in your CAD geometry, so you can't actually drive that up and down with a solver. Okay, the other sort of shape optimization relies on gradient-based methods, so adjoint techniques for using the relationship between the geometry and the parameters to home in on the optimum shape. So that requires that there is a connection between the derivatives and the mesh and the CAD geometry, and that is typically missing from most CAD geometry. It's another form of being a bit dumb. So there's a couple of challenges I can see from this one. So being able to reparameterize the CAD model to give it the correct handles for the solver to actually then start pushing the geometry around in a way that's going to reveal the optimum shape. And the second one is an adjoint friendly geometry engine, one the solvers can actually use for the differentiating the relationship between the solution and geometry. Okay, number 9. So this is another more obvious one. So not the manufactured geometry. Parts get manufactured, and there's going to be variances in manufacturing. That means that the produced product is not exactly the same as the CAD geometry. There's going to be geometry coming back from in-service, so things that have been worn or damaged. And with the advent of 3D scanners now, this is becoming more and more common that the geometry is actually coming at you from a 3D scan, so a point cloud or a tessellated point cloud, as you can see on the right-hand side here. So how do you integrate that into some of the more traditional CAE workflows which are built around CAD geometry? How do you marry them together? So there's a challenge coming out of this one for the integration of scan geometry into our current CAE geometry workflows. So the last one of the 10, this is a back to CAD problem. So this is the shape optimization follow-on. So as I was saying, CAE offers huge potentials for doing physics-based design, so really sort of homing in on the best design to solve the physics that you're trying to simulate. And that often ends up with very complicated meshes defining that shape. So for example, on the left here, we have a simulation of a sort of a hot to cold turbine blade. So the turbine blade is simulated in its hot running form, but it's obviously manufactured in a cold form. So you use a simulation to go from hot to cold. But the cold is defined as a mesh, not as a deformed CAD geometry. So there's a problem there. How do you actually turn that cold mesh into geometry that is good enough to put into a CAD system to manufacture? And on the right-hand side, here's our optimized cooling hole again. So that the mesh, the solver has been able to move the mesh around to find the optimum shape for this cooling hole. But how do you get that back into a CAD system again for manufacture, or into a format that you can share with another downstream workflow? Okay, so the problem here is that the simulation tools produce optimum shapes in mesh. They don't talk CAD BREP. They can't actually construct a BREP to describe their optimum shape. But CAD BREPs are the common denominator. They're the thing that allow you to exchange your designs very easily. So there are a couple of challenges here, I see. So the first one, sort of the hot to cold problem, you could imagine you've got a CAD geometry that's almost the right shape. So being able to actually just morph the CAD geometry to match the mesh is one challenge. But then in the other case where you have a very radically different shape, then you need to be able to construct valid CAD geometry from the mesh directly. So there's a couple of challenges coming out of this one. Okay, so that's the 10 issues with CAD geometry and why it's not CAE geometry. So just summarizing those, of all the challenges I pulled out, there's 13 of them across all those problems just listed here. So I picked out 5 of them as ones that are particularly top priority for us at CADfix. And some of these I'm going to be talking about in the second half of the webinar. But I think at this point, Marco is going to launch a poll to see if we can get some feedback on the relevance of these challenges.
Yeah, let's get our audience engaged here. I'm going to launch a poll. Go ahead and get that on the screen. Here you go. What we'd like you to do is, from the 5 top challenges that Mark identified, pick the one that's most important to you out of this list. And if you really have a pressing challenge that we didn't consider in this top 5, we would love for you to also send that to us in the Q&A window, and we can discuss that topic more when we hit our Q&A session here at the end. I know a lot of you submitted challenges as you registered, but if you want to, now that you've heard this material, send us anything else in the question window, feel free. We will leave the poll open here for just a few more seconds and see if we can collect any more answers. It's looking like there's a strong winner. I'm looking at some live results here, so I'm about to share these. I'm going to go ahead and close the poll, so if you didn't weigh in last second. Okay. All right, so here's our results. 62% of people agree that automatic simplification of CAD geometry is their biggest challenge, followed by 24% with automatic hex meshing and 10% CAD geometry morphing, just 5% with the more robust mesh generator. So
okay, that is very encouraging actually, that we do seem to have the right order at least.
Yeah,
so that's really good.
Go back here.
Yeah, so I'd be looking forward to seeing any additional challenges that we hadn't referenced or hadn't considered in the Q&A session at the end. But that's really good to see that we're talking about the right things here today. Okay, so I think that concludes the poll, and that was really useful. So thank you for taking part in that. So moving on to the second half of the presentation. So we have these 5 challenges I picked out for you to sort of vote on. But in terms of what we're focusing on at CADfix, there's a slight difference. We have those 5, but we also have this second one that I introduced, which is tackling that sort of dumb solid problem. So how do we get some proximity data into these CAD solids to allow us to do some sort of smart 3D reasoning? So there's that's one that I'm going to be talking about today. And actually these top 3 ones are the ones I'm going to show you some of the research and advances we've been doing in recent years. But before I get onto that, you might be thinking that if CAD geometry is causing such a problem, why don't we just switch to a different representation? Why don't we just stop using all these trim cells and use something that's better suited for simulation? So just to look at that question, so if we look at the other alternative representations that are in use today for various things, then we can see there's faceted geometry. That's very common. So STL files, for example. Spline geometry. So this is sort of the beginnings of CAD. This is the early days of CAD was spline geometry, but it's now coming back again with a lot of active research in academia to do with isogeometric analysis, a lot of spline volume for simulation. Subdivision, So this is very popular and very significant in the movie industry. So for animations and CGI, the geometry is nearly all held as a subdivision representation, not a B-rep, not a CAD solid. Point clouds, so with all the scanning data now available, point clouds are becoming quite a dominant form or a dominant source of geometry. And implicit geometry. So this is the sort of thing that is underneath topology optimization tools or generative design tools that are becoming more active in the last sort of few years. They're typically based on a different type of geometry called implicit surfaces. And then the last one is a CADfix special. So this is a representation that we've been working on for many years. It's called the medial axis transform, and it allows you to represent a solid by defining the skeleton and a thickness variation. So it's an alternative way of representing a solid. So there are alternatives to the current CAD geometry out there. So if we look at applications and what applications do we have that actually use the geometries and what geometries do they use, then we can see that facets are very versatile. So they're used a lot in these technologies. So gaming, VR, today's CAE, manufacturing, shape optimization. These applications typically don't work directly from the CAD geometry. They always convert that into a big pile of triangles, and then they start manipulating the triangles as their representation of the geometry. So these applications are already sort of one step away from the CAD geometry as their truth. Point clouds, so there's a lot of point cloud data being generated from medical scans, geological scans, QA and test type measurements. So there's a lot of geometry being produced that never goes near a CAD system at all. Splines, I've mentioned these are sort of more academic research, but they're looking promising for some of the future CAE capabilities, so the isogeometric analysis I mentioned. Implicit surfaces, so these are becoming available these days in generative design tools, shape optimization tools. They're using implicit geometry. They're not using any sort of CAD geometry. So medial axis, again, is a CADfix special. So we're using this to power a lot of our advanced CAE and advanced manufacturing geometry operations that I'll show you some of those later on. And subdivision, of course, is big in the movie industry. CGI is based a lot on subdivision, but it's now starting to also find a use in sort of shape optimization. So there's a lot of alternative geometries out there, and then most applications actually use an alternative representation rather than the CAD geometry that was created for them. But the problem comes with moving between these representations. So the green arrows here show the fairly easy transformations, how you can move between one format and another. So for example, going from CAD to facets, CAD to point clouds, CAD to implicit, they're quite straightforward transformations. You can move a CAD model into one of these alternative formats very easily. But things like subdivision surfaces, converting those back into a CAD is also easy. And splines as well, because of their history and their common history with CAD, is easy to convert those back into CAD. So, but the tricky ones are the missing ones. So taking facets back into CAD, that's hard. General point clouds back into a CAD model that you can actually get into a CAD system is hard. Implicit surfaces, so the sort of topology optimization results that we see, those things are also very difficult to get back into the traditional CAD format. So there's a lot of missing transformations here which sort of gum up the works really and stop you from moving your geometry into whatever format is the best one. So are we going to be replacing CAD B-reps? I don't think so for the short near term anyway. Primarily, it is very well established and it does work, as you can see by the growing complexity of geometries that the CAD systems can produce. It is a very effective way of defining a 3D geometry. So in conclusion, I think we are stuck with CAD geometry as it is today. There's a lot of legacy data. There's a lot of systems that are built around this. So the view we're taking at CADfix really is that we've got to learn to work with it. We can't sort of say, oh, just throw it all away and use a new system because it solves all your problems, because you break all these rules that we've got here. Okay, so that sort of answers the question of why don't you just change the problem and switch it to something else. So let's move on to the second half of the problem then. So we're back onto traditional CAD geometry, and these are going to be a couple of topics on how CADfix is trying to address some of those issues that I highlighted. So I picked out two of them. So the simplification one is the first one, and then the partitioning, so the thing that enables auto hex meshing is the second one. Okay, so looking at the complexity one, so this was problem number 2. So why do we have so many faces defining our CAD geometry, which then upsets the meshing? So just sort of a bit of background again as to how meshing typically works. So a lot of mesh generators have this sort of bottom-up approach, where you create your mesh by first meshing the vertices from your CAD model, then you mesh the edges, then you fill the interior of the faces, and then finally you fill the volume. So this is sort of a double-edged sword, really, because on one respect, you're exactly meshing the CAD geometry, so you're capturing the exact shape that was the design. But then on the reverse, that if the design or the CAD geometry contains any sort of nasty features, then they typically are forced into your mesh. So here's an example, a complex object here. If you zoom in on this top right-hand corner, we start to see the same sort of features that I was showing on the other one, where a lot of compounded modeling operations have resulted in a lot of faces, a lot of short edges, a lot of nasty-looking slivery faces appearing in the geometry here. So if you were to apply a sort of a standard meshing algorithm that would mesh each face one by one, then you would typically end up with a mesh that may look like this. And if we sort of zoom in on that top corner, we start to see these sort of odd hot spots of dense mesh appearing in the geometry, which at first glance you might think, oh, there must be some sort of geometrical feature there, some small step or some hole or something that requires that mesh in order to resolve the physics. But actually, when you zoom in on these hotspots, you find that actually they're there because of the very short edges, the very small faces, forcing the meshes to put small elements in there. And then because you can't, or you don't like to have big jumps in mesh size, you have to gradually dissipate that small mesh out across the rest of the object. And hence you get these sort of hotspots, little clusters appearing, driven purely by the fact that the skin was fractured up by the CAD system. So that's the problem. So just expressing it another way, if you were to take a cube and look at the cube, it has 12 edges, 6 faces. This is a unit cube, so the shortest line is length of 1. But if I was to split 2 of the faces, I still have a cube, so the volume is the same, the surface area is the same. The number of edges has gone up, now we've got 17. The shortest edge has dropped by half, we're down to 0.5. And if you continue that, you go crazy on the faces and chop them all up, you can end up with something like this. So we've got like 69 edges. But the key one is the shortest edge has dropped by a factor of 100. So if you remember, this is the sort of thing that drives the resolution in the mesh. So this is a big problem when you have the fracturing of the topology when the shape is the same. It's still a cube, all 3 of them in the cube. So the approach we're taking within CADfix is to implement something called virtual topology. So this is a concept that's been, which came from academia about 20 years ago, and it's been implemented in a few other systems. But basically, it involves grouping together faces that you would like to treat as one face. So it's easy to see on my cube example what I mean here. So the faces that I split up, if I could logically group them back together again and said, actually, just pretend these 2 faces is one face of my cube, and these 8 faces over here is one face of my cube, then the cube starts to look like it did before, which is 6 faces. So the goal of this work in CAD is to try and modify the topology, the number of faces, number of pieces in the boundary, to simplify it down to the bare minimum, to make it as easy as possible to mesh. Okay, so to do that, we need a couple of things. So if we group together a whole lot of faces, like on the left here with this car body, in order to be able to treat that as a single surface, the surface needs to have some sort of embedding geometry that gives it its 3D shape. And it also needs to have a parameter space that allows the meshes to walk across this very large compound surface that we've now created. So we need to have 2 things if we're going to make these virtual topology regions work for our meshing. So solving the first one, and how do we get the geometry underneath a collection of trimmed surfaces? So the approach that we've taken in CADfix is to create a triangular mesh on the CAD surfaces, stitch them together so the triangles are watertight, there's no gaps, so there's none of that tolerancing problem that you get with the CAD geometry. But we've also gone for using cubic or curved triangles, so we're able to get a very low facet count for the surface, but at the same time still capture to a user control tolerance the main geometry of the main shape of the CAD geometry. So that gives us a replacement surface that we can put underneath our zone, our virtual topology zone. So we need a parameter space. So best way to show what a parameter space is to sort of show how it works on this example here. So here's our complex part of our model again. We group together all those faces and we form 373 of them into one virtual topology zone. And the parameter space you can think of as being a quad grid, a piece of graph paper, for example, that you lay over the top of this collection. And that grid mustn't self-intersect, it mustn't fold, otherwise you can't mesh it. So there's the challenge. The more faces you group together, the harder it gets to lay out this quad parameterized space onto that geometry. But this is one of the areas where there's been a lot of advances in the computer graphics community, and we've starting to adopt some of those techniques to allow us to unravel the 373 faces. We can lay them out into a parameter plane where there's no overlaps. So our quad grid our quad parameter space on the left there has no intersections, no overlaps, and so it's valid as far as a mesh generator is concerned. And that's all you need to start meshing on this sort of simplified geometry. So here's some results then. So going back to the original case, there's the first mesh with all the hotspots showing up. Once we put all those 373 faces into one zone, parameterize it, and remesh it, then we now have this sort of mesh going on. So if I zoom in on one of the particularly nasty corners up here, you can see the dotted lines are the original CAD edges and the CAD faces. And you can see that the way the mesher has simply meshed over them as if it didn't even know they were there. But it has captured the curvature and the shape of the original geometry. So we managed to preserve the shape, but we managed to ignore the topology that was causing so much problems. So just one other small point on this, the triangular mesh that we were using as a replacement, we're actually able to, you might be worrying that actually we're not meshing the real geometry anymore, we're meshing this triangular approximation, but those triangular approximations actually contain pointers back to the original CAD face they were made from. So the mesh you see on the screen here is created exactly on the CAD geometry because we can project the mesh back onto those original faces to guarantee that the mesh is exactly on the designed geometry. So I think the takeaway from this first little example of our technology is really that the CA geometry doesn't have to be trapped by this straitjacket of CAD topology. You don't have to do destructive, collapsing, joining, modification of CAD geometry all the time. It still has its uses, but actually what you really want for automatic meshing is to be able to avoid all that manual intervention and automatically mesh over these sorts of small faces. So this is what we're hoping to achieve with this sort of technology I've just shown you, and it's looking really promising. Okay, so that was the first one. How do we tackle the simplification problem? Looking at the second one I wanted to show you about, this is partitioning and sort of tackling the auto hex problem. So for this one we're tackling two problems at once really. So we believe you can't do the automatic partitioning without having more proximity data. So something to solve the dumb solid problem coupled with something to actually create automatic partitions. So we're tackling these two problems here. And I've mentioned this medial axis geometry earlier on, so I've got a couple more slides just to introduce this so that you're aware of what it is. But you can think of the medial axis as being like a skeleton representation of a CAD face. So the two examples on the top right there are individual faces, and the purple lines are the medial axis geometry. So the medial axis, by definition, is halfway between the two closest boundary regions. So you can see how those purple lines are always halfway between the two closest black lines on the outside. And in 3D, it's the same concept, but you end up with a sheet geometry representing the medial axis. So that's that purple ribbon running through the middle there. Each face on that ribbon there is exactly halfway between two of those outside faces of your CAD model. So that's the medial axis in its simplistic form. Here's some examples of it actually being used on some geometry that might actually help. So we can compute the medial axis on the interior of an object, as you were just seeing on the previous slide, but we can also compute the medial axis of the volume around the object. So on the right-hand side, we have that simple solid there. If we compute the medial axis of the air around that, then we start to learn about the shape of the air around that object, and that's very valuable proximity data that we can then use for blocking and discretizing and partitioning that air volume around that object. So just a couple more examples of the medial axis on real models, again, to sort of confirm what you're looking at here. So here's a simplistic turbine blade, a single solid body, and here's the medial axis geometry that we've computed from that. So the geometry you see on the screen here is halfway between most faces. And in the bright red areas, this is the thickest part of that turbine blade. And the medial axis geometry carries this thickness property. So at any time you can say where is the two closest outside faces and how far apart are they. So you can see how this really fills that question about stumbling around inside a solid, not knowing where the nearest walls are. This tells you exactly where the shape of the interior of every solid or every air volume. And here's just one more example of an external fluid flow example. So a propeller, the fluid, the water volume around that, if you compute the medial axis of that water volume, then we get this sort of medial axis. So again, you can see the way that it gives you this sort of halfway bisector between the two closest parts of a CAD object, but it also gets quite complex when there's no obvious halfway point or there's no obvious opposing faces. Then it still gives you an answer. It still tells you the proximity of that and the shape of that region of space. So it's a very, very rich source of 3D geometry. Okay, so how do we use that? So I've got a couple of examples here. So a contact simulation. Typically a contact simulation has a lot of physics happening very close to the skin where the contact is happening. So you can see on the bottom right hand picture here an image of a simulation done on a contact here, and you can see the stresses are very localized to the skin, and the mesh you see there is a manually created hand-built blocked mesh. And you can see that to get the efficiency and to capture the physics in the most efficient way, they've gone for very anisotropic hex elements, very closely packed to the skin where the physics are. And then as you get away from those things, they transition into much bigger elements. So you gain the efficiency by focusing where you need it. So this is difficult to achieve if you're using a TET meshing approach, because getting the TETs to be very structured close to the skin is a challenge. And also manually blocking it up is also not a very good answer, because you've lost that optimization possibility there. You've got a man back in the loop. So another approach that you could apply to this sort of problem is the sort of the growing, the advancing front mesh generation process. So this might be the sort of result you get if you apply an advancing front mesher. So it's starting to give you the structured hex mesh elements close to the skin that you need. But when you start to look inside one of these teeth, you can see we have the same collision problem that we had with the aircraft model earlier on, where the mesh advancing from the two faces has collided. The collisions are too complex to be able to resolve, and so the mesh algorithm typically stops at that point, and the far field unstructured TETs in this case then have to sort of leak in and fill the gap that was left behind. So you're sort of degrading the area that you actually want to have the best mesh because of the collisions and the problems with the mesh generation. So the CADfix approach to this is we take the solid, we construct the 3D medial axis. So the colors on here are the thickness properties of that gear you see on the left-hand side. And then we use the medial axis to tell us how to partition the object such that we have a user-defined depth beneath the skin around the whole object. So you can see the multiple blocks we've created here, and they're all offset by the same distance. So if we sort of zoom in and have a look here, you can see the offset, the depth around the top of the object is quite constant. But then as you get into the teeth, where the opposite distance is actually beneath what we're asking for, then the medial axis gives you exactly where that collision front is. So you can guarantee to create the blocks and join them together without any sort of worrying about how to resolve those collisions. So once you can decompose your object into a collection of blocks, so these colored things are geometry, they're not mesh. So we've now got a whole collection of mostly cuboid bodies representing the skin of this gear tooth. We can then fit those with whatever mesh style we want. So obviously we want to have sort of anisotropic hex elements in the teeth, transitioning through pyramids, the yellow elements there, out into a tetrahedral far field for the best efficiency. Okay, so that's one example of using the medial axis to solve the proximity problem in order to get to auto partitioning, and in this case a hex dominant mesh. So the last example is doing this in on an air volume. So for CFD meshing is particularly keen on having very well controlled structured mesh close to the skin of your aircraft. And so there's areas on an aircraft that typically always cause problems with meshing. So this sort of collision of the fronts happens at junctions, around the wing root, around the tailplane, but particularly around the pylon, nacelle, wing junction. That's a very complex area. There's a lot of junctions and collisions and things being opposite each other. So you can imagine growing mesh from those areas. You get a lot of collisions very quickly. So again, the approach that we take is to construct the medial axis of the air volume around the aircraft, as you can see here. Sort of head-on view shows you, again, some of the nature of the medial axis. So you can see, if you look at the wing root, you can see that sort of skirt of medial geometry going away from the wing root, bisecting the gap between the fuselage and the upper surface of the wing. So it's always exactly halfway between those two pieces of the aircraft. And around the pylon nacelle junction, you can see how complex the medial axis is, but it tells you exactly how all those pieces of the CAD model relate to each other. So what's opposite what, how far away is something from something else. So given that very rich source of 3D data, we can then construct a blocking around the skin of the aircraft, again, to a user-specified depth. And then we construct this layer of simple blocks around the aircraft. Most of the blocks are simple cuboid blocks, so easily hex meshed. Others are 2.5D blocks, so if you can quad mesh the bottom, you can sweep them into a full hex block, or if you do a quad dominant mesh, you can sweep them into a hex dominant mesh. So here's a few pictures of meshes being created in those blocks around that aircraft. So you can see the different colors. The green ones are the hex and the hex dominant meshes in the blocks. And then we have a layer of pyramids that transition into a far field tetrahedral mesh. If we zoom in on the wing root junction, you can see that where previously you would have had some sort of pullback or some sort of collision happening between the advancing fronts of the wing and the fuselage, allowing the red tetrahedral to leak down into that boundary layer, this approach allows us to get perfect hex meshes into those blocked regions in the junction. And in this case, we actually done 2 layers of blocking. So we have the dark green and the light green on top of each other. So we can actually use this technique to go further away from the aircraft. But again, transitioning through pyramids into the far field TEDs. But again, you can see because we have the block structure close to the skin, that gives us very good control over the boundary layer mesh sizing. See that very black dense line there is very highly specified boundary layer distributions of mesh. So it gives you very good control over the mesh in that critical area. And just a last shot showing the nacelle pylon wing junction and how that has also been dealt with. Again, you can see the junction between the pylon and the nacelle. The pale blue block is where we've got full hex mesh, so no collisions going there to degrade the mesh. Okay, so that really concludes that part of the webinar. So the takeaway from this one really is that CAD geometry can be more than skin deep if you have something like the medial axis to give you that internal shape and representation and proximity data. And given that, you can then do some really clever, really advanced 3D operations on the CAD geometry. Okay, so just to sort of wrap up now, so going back to the beginning really and asking the question, are we there yet? So as far as geometry goes and computers, there's been some huge advances since this sort of thing back in 1982 to this sort of thing this year. So in terms of computer graphics, movies, visualization, we've made huge advances. We can fool ourselves into believing all sorts of realities now through computer generated graphics. But I still ask myself, is this thinking? Are they really thinking? Are they solving big, hard questions for me? Or are they just fooling my eyes into seeing some reality that doesn't exist? And when you start to then go back and look at this sort of physical testing, so the blade-off testing here and the physics that we're trying to solve here, and what we can do today, the best we can do today is still far, far short from what we really would like to do. There's a lot of compromises in the geometry. It takes a long time to do. So there's still a lot of challenges there to actually get this down to something we can put into an optimization loop. We can make it a routine piece of simulation. Okay, so that wraps up the webinar now. I've just got this last slide here just to bring back those 13 challenges that came out of the first half. And we'd like to open it up for a question and answer session now.
Yeah, if you have any questions that you've been considering, go ahead and send them to us in the question window now. I know our poll kind of showed we were already in line, I think, with a lot of the challenges that you all are facing, simplification being the number one. But if you had any other challenges you wanted to submit, now's the time. Otherwise, we're just a couple minutes over. We really appreciate everyone's time. Thank you for joining us. If you have a very specific use case or question you want to take offline, our contact info is going to be included in the slides that we send over to you here soon. There is a question here, will the slides be available? So yes, we will give you a PDF of these slides and then also the recording. I think if there's videos included, like your last one, it's very compelling with that fan blade, we can maybe send a link to where you can get to that video, because that would be very large for us to send.
Yeah, you can find that on YouTube if you look for fan blade off tests.
Yeah. Okay, well, I think that's it, Mark. Thank you so much for your time, and we appreciate you all joining us. We'll talk to you again soon.
Yep, thank you very much.
Okay, bye-bye.
Bye.